I'm attempting again to save this, try to do this on Zoom so that I can post it after class. Tell me how it's going, by the way, because I can do this great at home when I have a laptop and so forth, but with this computer, I can't connect directly to it. It's kind of a pain. But it's important you understand that what we're talking about here applies to data that looks like that when you make a bar graph. And there's lots of data that, well, didn't look like that. So just keep that in mind. I'll show you some examples in a minute. But I want to show you something kind of cool and at least help you understand maybe a little bit of advanced math. It turns out that here's the equation for a normal distribution. Mathematicians figured this out. If you take 1 divided by the square root of 2 times pi. Pi is a number that shows up with circles. What the heck is it doing here? And in an advanced math class, you multiply this by a number called e. And if that is raised to the negative 1/2 x squared power, whoa, easy there, partner. X squared power, you actually get a normal distribution. You get a normal curve. So I just want to take a quick look at this. So last time on your calculator, let's see, let's go 0. Last time on your calculator, we're using the calculator to give us areas under this curve. Does that make sense? We said, hey, what's the percentage if I said, let's go from a z-score of 1 to a z-score of 2, and we said, what's that area right there? Keep in mind that what's cool about this is we're talking about the area under that curve, but what's beautiful about this crazy curve over here, and that would take a lot of algebra to understand that curve. You've probably never seen the letter E before. That's kind of like pi. Pi comes up in circles and it's 3.14, so it's the symbol that we use for that. E is a number just like that. It's 2.718. And you got to study a bunch of advanced math to kind of understand all of that. Well, the brilliance of that shape right there is the area under that curve is 100%. And so what we're thinking of it as is not so much the area is 1, we're thinking of it as 100%. And so when we say, hey, what's the area under a chunk of that curve? Then remember, that's not just a percent to us, that's like the proportion of people that live in that chunk of the curve. And so remember, this only applies to normal distributions, but remember the graphs you've made in this class, lots of them are not normal. You have to have data that actually is normal. Now here's what's really cool. In Calculus 2, you learn about something called an integral. And so what I'm going to do now is ask it, what is the area from negative, and you should know the answer to this, what's the area under this curve from -1, a z-score of -1, up to a z-score of +1? Do you know the answer to that? What is it? 68%. If you don't know that, you have not been studying hard enough. So that's the empirical rule. Well, I'm saying, what is the area? We did this with the calculator the other day, but notice what that says right there. It says the area under that curve, and you don't understand the symbols because, and one of the reasons I'm showing you this is essentially a kind of a motivation, if you will, to study advanced math. Like what the reason we have this cool cheat buttons on our calculator is because some nerds took a lot more math than you've taken and took calculus and figured out this curve, figured out a curve that models normal shaped data. And this is calculus 2, taking the integral of an equation. And notice when we went from -1 to 1, we got that 68% that we've kind of memorized now. And of course, I could answer any question from your 7.1 assignment. Like if I said, okay, well, what if I go from -1.78 up to 2.3? So this should mean something from you from last time. So I'm going from -1.78, that's in here somewhere, so I'd be drawing a line there, and then shading everything all the way up to 2.3. Notice that almost goes off the page. So notice predictably, that's a really big number. That's almost the whole graph, right? So it's a little less than 1. So that's like 95% of people that would live in that group. And so it's sort of thanks to algebra, that's about 7 classes beyond the algebra that you've taken, that makes this kind of thing possible. So we're just using these cheat buttons in our calculators that some person's programmed in there, which is rather cool. So I show you that just because it's kind of at least neat to think, yeah, there is something in all those advanced math classes that does pay off for something practical. Interesting. Now, let's see. Let's just take a look at an example kind of right off the bat here. Let's see, which one shall we do? Let's do female heights. So I got some data that I scrounged up from somewhere about females' heights. Let's see, where did I scrounge it up from? 2019. This is a couple years old, so I scrounged this up myself. Now, would you agree that female heights, if we had a whole bunch of them, would probably be normally distributed? In other words, there's an average height around which most females, full-grown females, around which those most people structure, and then there'd be sort of less and less people that got really short or really tall. I mean, does that make sense? That would feel normally distributed. Now, so you know how to do this. I grabbed all this data. Let's see how much data is in here. Notice apparently 80 numbers. There's 80 different heights in this. And I cheated with Excel and said, what is the average of that? So there's the mean, and what's the standard deviation? Notice I did the sample. Let's change that to population. So there's the standard deviation. And of course, it's probably wrong to change that to a population standard deviation. Why would that be wrong?
It's not the sample.
What are you gonna say?
It's not all 5-year-old females.
If both those statements were right on the money. This is a sample, right? Are there 80 women in the world? This is a sample. That is not all the women. So that does make sense that that would be a sample. Maybe I'll put it back. Notice it's 3.11. Notice it just went to 3.13. It's not that different. So whatever, we'll leave it alone. Now, what you should have a really good feel for, write those 2 numbers down because I'm going to take this away. And notice, by the way, I wasn't paying attention. This is 5-year-old females in inches, so 44 inches tall. So this isn't all the this is 5-year-olds. And since there's 80 of them, this might be like one pediatrician's office or something like that. Does that make sense? It could be all their patients. If it was all the patients at that office, then I guess you could think of it as a population because you're limiting it to just that office. So I'm writing this down. 5-year-old . Five-year-old females. Maybe you've seen that symbol for females in a science class before. And the mean, we are told, is 42.22, and the standard deviation, we are told, is 3.13. And I'll go ahead and put the units in there, inches. And so, well, this is an important day to kind of make sure you're seeing the big picture of what statistics is really about. In one respect, we're done as of today with the majority of what people wish you knew when you left this class. There's another cool thing to do, and we'll do that, but this is it. Can you get a whole bunch of data like that? Could you make your own bar graph now? You should be really good at that by now. And if it came out normal like this, it's like, oh, cool, then that means we have some neat formulas that we can apply and so forth. And you should know some things about what it means now to be plus or minus 2 standard deviations and so forth. So you should know, since this is normal data, And by the way, in a sense, I don't actually know that. Do you notice I didn't have a bar graph at that? So it's like I would actually have to make a bar graph, because could that be not normally distributed? There are only 80 of them, and maybe it isn't. But assuming this is normal data, you should understand that the empirical rule applies. But what we've been learning recently is you don't have to just stick with plus or minus 2 standard deviations and so forth. So again, one of the big takeaways for the test is what is usual is to be below the mean plus 2 standard deviations, and above the mean minus 2 standard deviations. That's a big takeaway from this class, because again, we're talking about whether someone is okay health-wise, whether they're growing okay. So I'm gonna figure this out really quick. 42.22 minus 2 3.13s. I'm getting 35.96. And I'm going to write here the mean plus or minus. No, I'm not going to write that. This is more like X, like a particular patient. X. So that's the low end. And then this would be the high end, 48.48. And you may remember the data was rounded to 1 decimal place. So I could call this 35 well, I guess that would make that a 10. This would be 36, and that'd be 48.5. But again, the big takeaway of everything we've studied here is just to say, okay, if your child is in that range right there, then we're not worried about them, right? Things are good. They're growing normally. If they're a little shorter than this, then we're going to maybe pay attention. If they're a little taller than this, we're going to pay attention. Now, height is not a health thing, right? So we just find it interesting, but we're not going to treat somebody for being too tall or too short. So what we learned recently, though, is we would say, because of the empirical rule, that roughly 95%, again, was it 95.6? I forgot. Roughly 95% of the population will live there, right? You should be like mad that I'm talking about this because I've said this so many times, but this is the big takeaway. What we're really talking about now, though, is in chapter 7 is just, we don't have to stick with exactly plus or minus 2 standard deviations. We can kind of go any place we want with this. Now that we have a way, like I just showed you with Desmos in that graph, we have a way to find the area between any 2 shapes. Now, what I'd like to show you really quick is this. You already played with this function the other day on your calculator. If I go to second distributive and I say normal CDF, what we did with this the other day, and again, stare at your note sheet so you're ready for tomorrow's test. What does this function do? Does my note sheet speak to you? What is this function going to do for us? What's it spit out? I have a string of words at the end of it. What is this going to spit out for us? I mean, what does this function tell us? I don't mean in this particular case. So I said normal CDF dot 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 returns the probability between limits. So would you agree? I just picked a couple of limits right there. And isn't this the probability of landing in there? Isn't that the idea? So this is a percent, a probability. This is the proportion of people, 95% of people. If your child is a 5-year-old female, there is a 95% chance that they are inside this range somewhere. Does that make sense? That's what this is telling us. And so that's what this function does, according to my note sheet, is it, by way of reminder, is spits out a probability. Okay, well, let's use it for exactly what this says right here. So normal CDF, what does it ask for? It asks for a lower limit. I'm going to type in 35.96. It asks for an upper limit. I'm going to type 48.48. But this time, see, we're going to actually not just leave the mean at 0 and the standard deviation at 1, because in real life, the standard deviation and the mean are seldom 0 and 1. In this case, didn't we say the mean was 42.22? And the standard deviation was 3.13. Now, what is this going to give us for an area? Well, this is effectively the empirical rule. Like, it should give us that 95.6% or whatever it was. It's going to give us that percentage. I mean, that's kind of the point. Again, your calculator may not look like mine in terms of how you type this in. Your note sheet tells you the syntax, and it's typed right here. The syntax of this for older calculators is lower limit, comma, upper limit, comma, mean, comma, standard deviation. Again, does it make sense without a note sheet? You have to memorize that. If you put them in the wrong order, you're not going to get the right answer. So it says, sure enough, 95.4%, which is exactly what the empirical rule says, would be between two standard deviations, right? So the reality is in one respect, all we're doing different today is we're just not leaving the mean and the standard deviation at 0 and 1. That's it.
So what we work with today, if it falls out of the 65 or 95, should that be like a prompt in our head for doing something?
Yeah, well, what do you mean when you say 65? You mean
Or
68?
68, sorry.
No, not something wrong. The only thing that would be something wrong is if it's not somewhere between 0% and 100%. So, what probability is something happening? And so, but again, let's use this now for, and I'll go ahead and write in what I just said. So we typed norm CDF cumulative distribution function. Whew, that's a ridiculous mouthful. I love this pencil, but it doesn't seem to like to give me lead. So I type lower limit, comma, upper limit, comma, mean, comma, standard deviation. And sure enough, it spit out 95.4% or 0.954, just like we sort of knew it would.
So why
Would yours what?
I typed in the same exact thing.
Uh,
0.9605.
Maybe I didn't type what I said I typed, or maybe you didn't type what you said you typed. Let's double check. Let's get to the bottom of that. Did I type what I thought I typed? It looks like I did. Did I? Okay. Thank you for asking that. Ask immediately. But you see what's powerful about this now is I can answer kind of any question I want. I'm not just stuck with, well, you didn't need this button to know that that was 95%. We had memorized that from before. We were stuck with plus or minus 1 standard deviation, 68% of people, plus or minus 2 standard deviations, 95.4% of people, plus or minus 3 standard deviations, 99.7% of people. We're stuck with that. All that's changing in this section, we're not stuck with anything. We can find any percentage we want. So what if I ask the question, find the probability in this scenario, find the probability that your child will be taller than 40 inches at 5 years old. It's no different than what you did in 7.1, which is good because this is really powerful, but it's also challenging, and I wanted to have more time to kind of soak in. You don't actually have to know anything different than you did in 7.1. Taller than 40 inches. Again, draw a picture of this just so that you kind of make sense of it. The mean is 42. So I want you to think about this. This is kind of cool. Everything we did the other day, the mean was centered at 0. Well, the mean was always going to be right here. Does that make sense to you? In the normal distribution? Because if that's the most likely event, that the 5-year-old is 42.22 inches tall, that's going to be the number around which all the children crowd, right? They're all going to be a hair taller than that, a hair larger, right around there. And so this is the same graph we looked at the other day. It's just not centered at 0 anymore. So everything on 7.1, it was always centered at 0 because the mean was 0. Well, now this is going to be centered at 42.22. And again, you kind of have 1 standard deviation and 2 standard deviations, whether they're physically drawn in or not. But in this case, of course, standard deviation would be 3.13. So I'd actually have to add that to this in order to get that location. But we don't really need to do that here. All I'm saying is, can you estimate, now that I've drawn that a little bit, can you estimate what kind of a probability or a percentage or a proportion of the population is going to be taller than 40 inches? Well, now that I told you 40, does it make sense you know that, oh, 40 is over here, but then I said taller than that, right? And I don't know exactly where to put this, but maybe right there. And because I said taller, I'm basically shading to the right of that. I didn't say shorter. So we're kind of concerned with that number right there. We're concerned with that, what ultimately is an area. My point in drawing that is, does it make sense that we know that from here forward is 50%? And there's a little more than that. So the answer to this should be more than 50%. Now, is it 52? Is it 58? Is it 67? Is it 72? Maybe I'm not exactly sure how much more that is. But again, don't just be pushing calculator buttons. Type stuff in. Now, this command asked for a lower limit and an upper limit. Where's the lower limit on your graph? Where is it always? Some of you were screwing this up the other day. Where's low numbers? That way, right? Low numbers are that way. So that's our lower limit. Sorry, that is 40 inches, right? What's our upper limit though? How far does this go? It goes forever. So what am I going to put in for an upper limit for this? Norm CDF, lower limit, 40. What am I going to put for upper limit? Notice this is a little weird. The other day we just put in like 4 or 5 or something like that because that was a z-score. You can't just put in a z-score of 4 now because notice 42 is here. So is it 50 inches? Is that far enough? Well, notice 48 was 2 standard deviations away, so it's got to be more than 48. Again, just make sure it's huge. Put 1,000 in there. They're 1,000 inches tall. They're not going to get that tall, right? Now, you may have noticed in the book, they have there's a way you can type e to the 99th power, which is sort of like putting infinity in there. But I just think without knowing what e is, I happen to mention the same exact number to you today, e, and sometimes your calculator has that number sitting in there. That's kind of code for large number. I'd rather you just make some sense. Some huge number. But does it make sense that huge number has to be in context? I can't just say use 1,000 every time. Because what if we were breaking beams and the beams were breaking at 1,000 pounds and 1,200 pounds and 1,500 pounds? Now all of a sudden the big number is like 50,000. Like, think about it a little bit. Remember, what we really need to do is be out there at like 5 or 6 or 7 standard deviations away. So if I added 5 of these standard deviations to this number here, which again is a total waste of time. If I said 42.22 plus 5 of those standard deviations, does it make sense? The number like 60 would have been far enough here. Now I know that. I'm saying that's a waste of time. Just kind of look at your numbers and say, oh, we're in the 40s. Well, then I'll put 1,000 in there. and then I won't have to worry about it. So I'm going to put 1,000 in there. And then what's the mean in the standard deviation? Same thing there. And for this problem, every single question is going to be the same mean and the same standard deviation. Again, what am I expecting for an answer to this? More than 50%. So 40 inches, 1,000. Notice I'm reusing this. I still have the mean and the standard deviation in there, so I don't have to type those in again. And sure enough, it says, ba-bam, 76%. Notice that's a lot more than 50%. My guessing wasn't all that great. As a side note, would you agree that 40 is 2.2 below 42? And 2.2 is a decent chunk of one standard deviation. And since you may remember, one standard deviation to the left was half of that 68, 34%. I didn't quite make it to that line, so I didn't get all of the 34%, but that's a pretty big number. No wonder it's so much more than 50. So but again, what I'm really concerned about, or probably more concerned about, is not have I successfully taught you how to push buttons, but can you act on that number? Like, does that number mean something to you? You understand what that's telling you and why this is a powerful thing? You understand it's telling you 76% of kids will be more than 40 inches tall by age 5? Now, 76 is a pretty good size number, but remember Q, what's the probability that they're going to be less than 40 inches tall? But I guess be 24%. That's a big number. So it's like if my kid is smaller than 40 inches, I'm not going to go, oh no, what's going on? Now, I want to tell you, actually, let's just do another similar question. What if your kid was born, your kid, and they were so what if your kid was 37 inches tall at 5 years old? Now, because the mean is 42, then it's like, oh, my child is on the shorter side. But you just kind of want to understand, and by the way, this is what pediatricians do. Actually, somebody tell us here, some of you have kids. When you go in there, what do they explain to you about your kid with respect to weight or height or some of their health? What do they tell you about where they are?
He's in the 40 to 50 percentile or whatever.
Percentile, have you all heard that?
Yeah.
They're in the 40th percentile. That's a part of this next test. That's a part of that's the big takeaway here from this entire class, because that's exactly what they tell you. They tell you what percentile your kid is in. What we've been doing lately is just saying how many standard deviations are they away. We'll say like their z-score is 2, so they're 2 standard deviations above the mean. But isn't that complicated? Like, you have to know some stuff like you do in this class to understand that. If you turn to a parent who hasn't taken this class and said, your child is 2 standard deviations above the mean, they're going to just turn their head sideways like a dog and not know what you're talking about. And then you'll either have to sit there for 45 minutes explaining to them what that means, or give up. So they use percentile, and you're now in a spot to answer that question. So 37 inches tall. Now, does it make sense you could figure out based on these standard deviations up here? You could actually figure out what their z-score was if you wanted to. Let's do that really quick, just for the heck of it. Z-score is found by taking your kid, your x, your variable, minus the mean divided by the standard deviation. Because that's how you tell how many standard deviations you are away from something. So my calculator says that that is negative 1.7. Now you, because you are trained in statistics, actually know what to make of that, don't you? If you don't, again, you're not studying hard enough. Because, oh good, it's not -2, right? So they're not unusual. They're short, but that's not unusually short. As I said though, all we have to do is apply what we did today, and now we can explain this to a parent in a much simpler way. So we want to locate this kid, and so again, you don't have to draw this, but you're at least thinking it. And now that we know that's negative 1.7, it's like there's your kid. Your kid's right there. 37 inches tall at age 5. Does it make sense that divides the 100% into 2 percentages? And if you were to guess, I would hope you would say, well, that's not very big over there, as this works its way to 0. So maybe that's like, I don't know, 6% or something like that. And if that's 6%, then of course this area over here is going to be 94%. Does it make sense? They divides that one score, kind of divides the percentage in half. Now let's see what it actually is. Instead of me just guessing 6% without thinking that much, let's see what it actually is. Now, does it make sense you could do this either way? Do I want the area on the right or the area on the left? Doesn't really matter. I'm going to do the area on the left this time, just since we did the right last time. So again, I ask you the question. I hope you can already do this. I hope you don't need me to show you. You know, what should I type in here for my lower and my upper limit then? So where does 37 go? Some of you were screwing this up again the other day. There's my area. That's the upper boundary. That's the lower boundary every single time. So 37 is the upper boundary, isn't it? That's why you got to draw the picture, at least in your mind. If you're sharp, maybe you don't have to physically draw it. 37 is actually the upper boundary. What am I going to say for the lower boundary then? Yeah, 0. You can't be 0 inches tall, right? Negative 27, like just don't say 36. It's got to be way out there in the tail somewhere, right? 0, great answer. Some small number. No reason it couldn't be negative, because remember this graph actually goes forever in each direction. So I'm choosing to find the left area. So norm CDF, some small number in this case. My right boundary is 37 and my mean and my standard deviation are unchanged. The question is, do you get something that doesn't surprise you? Are you just a button pusher? Or are you getting something, well, kind of like I did, like a small number, like 6%? Are you getting something that makes sense? Notice my guess wasn't terrible. I got 0.4047. Now, this is a good place because this just randomly happened. Is that unusual? You can answer this right now. You don't need to think about mean plus 2 standard deviations. Remember, 2 standard deviations was 95%, therefore 5% is unusual. If you are in a group that is less than 5%, that's unusual. That child is a little on the unusual side in terms of height. But notice that's really close to 5%. It's not like they're crazy unusual. That's just something to think about. So 0.048. So I'm actually going to fix this now. And again, don't you automatically know the right answer to the other side since all the probabilities have to add up to 100? So I guess that'd be 0.952, I think it would be. Notice I chose not to write them as percents. I just thought I'll just write them as decimals. So it's basically 4.8%, 95.2%. or 5%, 95%, pretty close. This child is in the 4.8 or 5th percentile. That's how percentiles work. Always left. It's always left. You always do the left one. What does it mean to be in the 5th percentile? The doctor says your child is in the 5th percentile. Based on this picture, what does that mean? Exactly. It means they are taller than 5% of the people, and 95% of the people are taller than them. Remember before when we did the 5-number summary, and there was quartile 1, quartile 2, quartile 3, and all that? And so that was really the 25th percentile, the 50th percentile, and the 75th percentile. What's cool about this is now it's even more accurate than that. You can kind of put them exactly where they belong, just based on this number. So you don't have to say they're in quartile 1, because that's pretty broad. Does that make sense? If I was told my child is in quartile 1 with respect to like vision, something, they're 5 years old and I can't really tell if they can see. Is that weird? And the kids that can't see, you actually don't know, they can't see. They function okay and maybe eventually start banging into stuff. Or they can't read. That's a 6 years old, they're learning how to read and they can't seem to learn, and then you discover for the first time, oh my God, the kid can't see, because they don't know that they're different, right? Then you put glasses on, all of a sudden, oh my God, they can see. So if I was told my child was in the bottom quarter of people that could see, my immediate question would be, where in that quarter are they? Are they at the top of that? So they're, a lot better off, or are they actually clear at the bottom? That's not very descriptive. So that's why we use percentiles. If they told me my child was in the 2nd percentile, then that means there's only 2% of people whose vision is worse than them. And so I know, oh my gosh, they're really low. If they told me they're in the 24th percentile, though, that means, well, there's a quarter of people actually have worse vision than they do and less stress. You see why percentiles are used? It just tells you where you land. This is, again, one of the biggest takeaways of everything you study in this class. You got to understand mean and standard deviation to get this. But as soon as you turn it into a percentile, that allows you to tell somebody or yourself, where are you relative to other people? What percentile are you in? If you're in the 70th percentile, that means you did better than 70% of people, and automatically 30% of people did better than you. Does that make sense? Let's do some more examples. So this seems like a fun one. Roller coaster wait times. You're waiting in line for the roller coaster. Again, I would say, do you agree that if they collected lots of data, like 2 years worth of data, that the wait times would probably be normally distributed? Occasionally on some super busy day, you'd have to wait forever. On some rainy Tuesday, maybe you don't have to wait at all. But there'd be a cluster of waits that are kind of around the average time. So you'd be able to collect that data, right? I mean, you're supposed to be the person at the park that can do this kind of stuff now. You can make all these calculations. And it'd be kind of cool to know that. I seem to have this memory now. It's like that's why I was at Disneyland. Aren't there all these apps and stuff now? You can kind of know what the wait times are all over the park based on where people are standing. And, there's all this information is kind of live. And so, of course, naturally, if there's some ride like this and I have to wait an hour and a half, I'm thinking, geez, I paid $200 to get in this stupid park, and I'm just going to stand here for an hour and a half, my 8 hours, waiting to get on this one thing. It's like, I'm going to go to the beach. So, and also be thinking a little bit, because we're about 2/3 of the way through this course, you have a final project to do in this class where you're going to gather data like this that's interesting to you. Again, you can gather it yourself, in some way, like put out a Facebook post to people that you're connected to and ask them some question, you know, how many hours a week do you watch television? How many times, how many text messages do you get a day, whatever, something, find something interesting to you. It's probably the funnest if you collect it, but I certainly don't want it to cost you a lot of your own time. But you're just going to collect a bunch of raw numbers, and notice that's raw numbers. They're all, you know, out of order. So apparently that's minutes. Notice there's no label there. And so you should be able to make a really nice looking bar graph for that now. You got to choose your own classes. You got to choose how many bars do I want to have on the bar graph. And if you did that, I would expect this one probably would have that normal distribution kind of look. Again, you're not going to see a curve like I drew up there earlier. You're going to see a bunch of bars that are all next to each other and have that normal shape to it. But what about now? So again, I just figured out how to do something kind of cool here. I'm going to show you how to do it because I just watched, there's 100 pieces of data here. So you know how it takes forever to kind of drag down on something? Well, this isn't terrible, but I just read today. Let's see, what do you do? There's an end button on your keyboard, which I've never looked at before. So I click end. I think I got this right. And then you hold down shift and then hit the down arrow. I just selected everything. That's kind of cool. The reason I looked at that is I'm going to show you some data in a minute. There's like 3,000 numbers in the data list, and if I have to drag down, I tried that, and it was like 30 seconds in, and I wasn't even halfway to the bottom.
How do you do that again?
Yeah. So you hit, and I'm going to do it. So I need two things here, right? So I need the average equals, I need the mean, which again, Excel calls the average. And so now I need these numbers, right? So if I click that top cell right there, and then I hit the end button on the keyboard, which is kind of over on the right-hand side, and then hold the shift button down and hit the down arrow. Can't believe how much I've used this and I never figured out how to do that. So don't screw this up. I've talked about this a lot, but I've never held you to it. How should this be rounded? What should I call that? Nice and loud. You should all know this, but I've never busted you for not doing it right. What's the rule of thumb? 1 decimal point further than the data. So I'm going to use this little decrease the decimal. I just made it do it for me automatically. So there's my mean. And again, other cool tricks. Now I need I'll just abbreviate this. Now I need the standard deviation. So what I'm going to do is grab this formula up here. I'm just going to do it from scratch. Equals standard deviation. Is this a population or a sample? Tricky question, but think about it. I didn't ask that flippantly. Is this a population or a sample? Most likely it's a sample, but could you dream up a scenario where it's a population? There's lots of them. One of them is it could be just, this is Tuesday, November 12th. That's like all the people that wrote it. Or it could be you've written it 100 times and those are all your wait times. So that's every piece of data there is. I'm going to use population, but I don't really care. And again, let's see, click, hit end, shift down arrow key, bam. I like that. Oh man. And again, rounded to, so I can look at that and say it's 3.4, but just let Excel do it for you. Notice it automatically rounded correctly. So that's a little unfortunate that those are almost the same number in terms of us making sense of this. But again, remember at the start of this class when I showed you the formula as to how to calculate the standard deviation? Remember how horrific that was? Again, no one's going to ever want you to do that in the real world. They're going to want you to do this. Like let the rise of the machines take over. I have the mean and the standard deviation. Notice that's kind of weird because one standard deviation below the mean, you're already at 0 minutes. So notice it's kind of impossible to wait unusually short period of time. Again, we are assuming this is normally distributed data, which you can't really do in the real world. I would need to make a graph of this and have a look at it. And probably 100 pieces of data might not be enough to actually show that it's normally distributed. But again, let's just play with that a little bit. So I'm gonna make a third example here. But I would like you to answer this question. If you waited, say, 65 minutes, you'd probably be pissed off, right? Well, you wouldn't be pissed off unless you knew the average wait times. You would just think that's the way it is. But if you waited 65 minutes, what I'd like to know is, can you tell me the percentile, that particular score? You waited, you don't care about all these other times, you care about your time. And you waited 65 minutes. What percentile were you in? What percentile are you in? That's the questions I'm going to answer here. Switching screens. Every question here just pertains to finding the area under a curve. And right in the center of that normal distribution would be 30.7. Roughly, do you agree that one standard deviation, 30.4 above 30 is roughly like 60, 61, and we're a hair above that? So we're like a little more than one standard deviation above the mean here. Whatever. Do you understand why I called that X? Because I think that's sometimes confusing. Why is it X? Because X is a variable. So I waited 65 minutes, and then you came the day later and you waited 120 minutes or whatever. That's a variable. The mean and the standard deviation, not variables, but it's variable in terms of how much wait time. Again, what's powerful about statistics is we are predicting something here. Keep in mind, what I just talked about is what's my percentile because I waited 65 minutes. But here's a better question. The park closes in 80 minutes. Should I get in that line? I'm trying to predict the future here. Am I gonna wait in that line so long that I finally get to the front and the park is closed and I waited my last hour and a half and I just have to do nothing? This is decision making now. We're not reporting on the past, we're actually predicting the future. Should I go stand in that line? What's the probability that I'll wait 65 minutes and then park closes and I don't even get the ride on the ride? If I ask for percentile, what area am I after? The left. Because percentile is always what percent of people are you above? So I'm looking for a percentage. That's what norm CDF does. My lower limit. Again, what should my lower limit be here? This one's interesting. It'd be tempting here to say 0 because you can't wait less than 0. However, remember that graph keeps going. And one standard deviation below this graph is 30, which means I'm at 0 with just one standard deviation below the mean. Does that make sense? If you said 0, although that makes sense in real life, this graph keeps going. So you can't put 0 here. You got to put negative 1100, some giant number, negative 2000. So never be afraid to just put a really giant number, which is kind of the why the book always says use e to the 99th power or something like that. But just be careful with that. It's got to be a really big number. Maybe we'll look at that and see in just a second. So again, I'm looking at this graph. Your lower limit on the left is over here. This is my upper limit. So I'm going to say negative 1,000 for no good reason. But remember, what you need to be is at least 5 of these below this, right? 5 standard deviations is crazy small. 5 of those is 150. If I go 30 minus 150, I'm at negative 120. Negative 120 would have been fine here too, now that I'm thinking about it. But this is kind of a good example because a lot of us, myself included, if I didn't slow down and think about this, I would have put 0 for the lower limit. But remember, these go forever. Upper limit 65, mean 30.7, standard deviation 30.4. I stick all that in, beautiful things happen. Again, I know I'm above the mean here, so I better get some answer more than 50%, significantly more. As I said, we know we're more than 1 standard deviation above the mean. And we know that if this was 1 standard deviation, that's 34%. So if this is 34% and left is 50%, that's 84%. I actually know my answer is more than 84%. Again, I think it's just cool to be able to think, not just mindlessly push buttons. So I already know the answer to this is more than 84% because this is more than 1 standard deviation above the mean. So I know the answer to this is going to be more than 84%. So negative 1,000, comma 65, comma 30.7, comma 30.4. Double check before I type this that I entered all that in right. Looks like I did. Hey, look, more than 84, 87%. So I got 0.87, which means hence the 87th percentile. So if I had waited 65 minutes, I would now be kind of bummed because it's like, man, I waited longer than 87% of people that have ever taken this ride. Man, I really got hosed. If I was standing there thinking, should I go wait in that line because the park's going to close in say 70 minutes, I would say yeah, because 87% of the time it's less than that, so I'm probably going to make it. There's only a 13% chance that it's going to take longer than that, and then I'll end up standing there and not get to go. You see what I mean? You see why it's so important? This is predictive. We're not talking about reporting on the past here. We're talking about making decisions. Should I invest in that company? Should I go wait in that line? This is basically saying you have an 87% chance of making it onto that thing before they close the park. Oh, okay, I'll take that odds. Let's do it. Now, there's a 13% chance you don't make it. Is 13% unusual? It's not. So if you didn't make it, you should say something like, well, I rolled the dice and came up short that time. Remember, 13% is a number. 13% of people are going to wait longer than that. That's what this is saying.
So
Go ahead.
with this, then in this scenario, it's hard because like when my brain hears the 87%, it's like, oh, that's good. But you kind of want to be more towards like 50%, right?
Yeah, well, the problem is sometimes you're measuring something good and sometimes you're measuring something bad. Like if it was IQ and we're in the 87th percentile, it's like, yeah, 87%. But what if it's like cancer? I don't want to be in the 87th percentile of getting cancer. So it kind of depends on whether you're talking about something negative or positive. Now, in this case, that's negative. Waiting a long time is negative, which is why being in the 87th percentile for wait time is actually bad. Shelby.
Could you refresh my memory as to why, like, on page 1, page 1, and we don't put in the 0 or 1, like the section before?
Yeah, so let's scope this out. So let's go back and redo that and put in what would make sense to put in, which is 0. Notice how bad of an answer that gave us?
Well, I mean, like the mean and the standard deviation between 0 and 1.
Oh, got it. So when you have a Z, when your information is a Z-score, Notice in this case, our information is here's my wait time, here's my mean, and here's my standard deviation.
So it's giving you that, so that's why it's just based on.
Yeah, so it's basically saving me the trouble of having to calculate the z-score. So watch this. This is kind of interesting. We'll come back to what I just did in a second. If I calculated my z-score, 65 minus 30.7 divided by 30.4, then my z-score is 1.12. So I'm 1.12 standard deviations above the mean. Now that I know that, I could have done this with 7.1. I could have said, okay, I could have said normal CDF, lower limit. Notice I'm using a z-score of 1.12. So my lower limit z-score, I'll say, is -5. My upper limit was 1.12. My mean is 0 and my standard deviation is 1. Notice I got the same 87% I just got a second ago. What's cool about today is I don't have to calculate the z-score. In reality, 7.1 was just prepping you for today because you don't walk around just knowing your z-score. Don't you have to calculate it like I just did? And so why calculate it if this normal CDF button just lets you type in the mean and the standard deviation? It kind of does it for you. You see the logic in that?
Yeah, I'm just like looking at it like a problem. I don't.
No, that's a wonderful question. Now, are you surprised by the fact that, and by the way, why didn't I get the exact same 87? Well, that's because I only went to -5, and I should have maybe went a little further than that. And also I rounded off 1.12, but it really was 1.13, wasn't it? I did a bad job rounding. That's why the answer was 86.8 instead of 87. Why is this answer so bad? Like I only went from 65 to 0. Why is that so bad? Because you can't wait less than 0 minutes. Well, I don't know as you have to know this, but I think I want to show it to you anyway. Just to kind of help you understand that typing in 0 is a little bit dangerous. We need to take a break here in a second, but. So I'm going to go back and show you the graph of this. I think I have this right. So a minute ago, so that's where the standard deviation goes in this equation, as it turns out. Again, you don't need to know this, so don't freak out. And instead of x squared, maybe you recognize this, x minus the standard deviation, I'm sorry, x minus the mean, which was 30.7. Divided by 30.4. Do you recognize that as the z-score? X minus the mean divided by the standard deviation? Like that's a part of this formula. I think I have this right. Really complicated formula. Actually, I'm worried I don't have it right. X minus mean. Notice it doesn't look like it has a bump in it. I think that's because it's so tiny. Maybe this was a bad idea. There we go. Notice this is a really interesting normal distribution in the sense that it doesn't have a really steep peak. But the point is, the point of showing you this is notice there's still area left of 0 here. Does that make sense? So when I went to 65 to 0, I only got the area to right here, but there's a whole bunch of area over there that was lost. That's why you have to be careful, because this graph literally goes forever. Let me make the graph a little more descriptive. There. That looks a little better now. Do you see why if you go from 65 to 0, you're only going from here to there? Well, look at all that area you lost. So the mean was actually right here. Notice the mean of that is indeed at 30.7, but if you go one standard deviation below 30.7, you're basically right here. That's only a z-score of -1. Notice in this context, you don't just see 0 and then -1 and +1 and -2 and +2. You're literally seeing wait times here. What's kind of cool about looking at this graph is notice 110 minutes of wait time. There's some area over there, like you might wait 110 minutes. Ooh, that doesn't seem really fun. Let's figure that out. What's the probability of waiting more than 110 minutes? This is exactly the type of questions I'll be asking you on the test tomorrow. I'll say something like roller coaster wait times are normally distributed with the mean of 30.7 minutes and a standard deviation of 30.4 minutes. What's the probability that you would wait more than 110 minutes? And again, the idea there is the park closes. I got 120 minutes. I got 2 hours and I want to ride that dumb ride. What's the probability that I'm going to get to ride it before the park closes? $110, is that the lower limit or the upper limit? Think about that. So I want you to actually get an answer to this, even if it's wrong, and then compare it to your neighbor. Especially if you got the same answer, then you probably suddenly feel pretty good, like, hey, good, we got it right. However, it could mean you're both wrong. Like, compare with some people around you and see. But remember, look at this picture up here. You better expect a pretty small percentage. The area under that curve is always 100%. How much of that area is more than 110? Tiny. You better get a tiny percentage, right? You should know that just based on the picture of this. This is why you draw this. You get 25%, you got it wrong. There's no way it's that big. Maybe you notice with this graph that by the time I'm out here at -100, I'm pretty much at 0. And when I'm up here at 160, I'm pretty much at 0. The graph is flattened out, but notice it keeps going forever. If I zoomed in on this, this graph is still above by a teeny bit. I ask you again rhetorically, how much would you bet? This is just a great way to think about math when it comes up in your life. How much would you bet your answer is right? If the answer is not 90 to 100% in the real world, then you phone a friend. Like, just don't go build the bridge if you'd only bet $20 on the $100. You have $100 to bet and you're like, oh, I bet 20. Well, then don't go build the bridge. Don't go wait in that line. Don't buy the stock or whatever. Because you know that you don't know. Good, you know that you don't know. Then call somebody else and get some advice, your nerd friend or whatever. It's when you don't know that you don't know. Yeah, let's buy that stock. Oh, let's go wait in line. Oh man, the park shut down. Like, know that you don't know. It's actually okay. In this class, if you know that you don't know, are you just going to show up tomorrow and let it wash over you and not like come bother me? You shouldn't be bothering me outside of class so that you can know. Hopefully, you agree that the left-hand limit, the lower limit is 110, because I said more than, so that means the upper limit, and I chose 250, just because the graph seemed to show that that was high enough. When I did, I got a predictably small number. Notice I would go wait in that line. Like if I really wanted to ride, it's like there's only a 0.4% chance. That would be outlier unusual for me not to get to ride the ride. So I'd go wait, and I'd be able to be really pretty darn sure that I'm actually going to get on the dumb thing. Does that make sense? Shelby, you had a question?
I just kind of like worked it backwards. I guess I was curious if that's going to give me issues in the long run. I just did the 1,000 and then the 110, 0.7, and then I just deducted that number from 1 because if I know what everything to the left is, then I know what's left.
Good job. In other words, you sort of found the percentile. You went negative 1,000 for the lower limit, and then you went up to 110 for the upper limit. And so that gave you not the right-hand percentage, which would have been the easy way, but it gave you the left-hand percentage. As long as you understand that percent, and it sounds like you do, that percent is not more than 110 minutes, but it's actually less. Now, in a sense, to your point, does it make sense? I basically have a 99.5% chance of getting to ride the ride. So could you look at the left side of that? Sure. It's a question of, am I thinking about my chances of getting to ride the ride or not getting to ride the ride? Based on the fact that I said more, I was thinking of in terms of what's the chance that I won't get to ride that? Oh, that's less than 1%. I'm doing it. That's probably not going to happen. You were saying, what's the chance I'll get to ride the ride? Now, in a sense, do you agree that's the 99.5th percentile? So if you went to that park and you waited 110 minutes, bad news, you're in the 99th percentile of the longest wait times of people that have ever ridden this ride. There's only 1% of people that have ever waited longer than you. So to your point, it's kind of cool because you're locating yourself on this normal distribution, and then it is a question of which part am I paying attention to? They're both true. Okay. Let's take a break. And all I really want to do is do a few more examples, kind of look at the online homework. Is there a reason we should do inverse normal here? Because we have kind of two commands we used the other day. We have some inverse normal questions we need to look at. So awesome. And I'm obviously going to stay here and help you with problems if you're on your mind right now. What's that?
You know, 10 years is Zoom today.
I'm recording this right now.
Oh, okay.
Oh, you mean tonight?
Yeah.
You meant tonight. I would say 6 to 7 or 7 to 8 right now to me. Let's do 6 to 7. I got a print one at 7, I just realized, so we're going to ignore him and make sure we're in statistics. Yeah, let's do 6 to 7 tonight. So I'll send an email out with the link for that. So again, that's just optional prep for the test. Go ahead. Yeah. Yeah, do you know what happened? Like what happened there? You know? I remember looking, I forgot where I did a whole bunch of shit.
Yours wasn't you, like typical you. Oh, so you thought you were done, but maybe you didn't get saved and then you sent it to me. So that's what you're saying. Yeah. So I would, you've proven yourself to something else. Yeah, send it again, then also. Like, tell me an email, okay? So it's done today. James will be right there. Good. That 87, which exactly 87, 95. Yeah, so. Yeah, see. Yeah. That's gonna do 85. Now, does that work? Notice it's not less than. 85 plus 6. 85 included. Down, probability of people. So the reason I say lean forward is because the reason I say lean forward is because that's equal to CG. Therefore, you subtract it. So the tricky part about this is this. You're talking about people showing them. Now, what you could have done this instead, but I said you have people more than. You either have to- yeah. It's gotta be.
No, it actually. They said it was, not worried about it. And then I think that other one. Yeah, I think the two would be unusual.
Yeah. So if it was more than deviation, it's good to say about more than.
And then there makes two. deviations that-
I kind of knew what you were talking about, I did say. But even saying something even simpler than that, which is just a standard deviation, like as soon as you know that you, again, that's your best guess, it's also. Probably maybe not to show up. In my case, no. That's the best guess, but to be able to say it would be super common for it to actually deviate from that to 6. That's very different than somebody saying.
I get what you're saying. Okay, thank you.
Title of it, like it's 6 out of 32. Oh, we tested on it.
One set of computers is Not the labs, but yes. Yeah, we're trying to end in homework. I go in there, I can't, I graded I know I graded the ones that people physically handed me. I'm not sure if I got your handed homework in my open math later last night. It might not be there. Except the lower limit's got to be low. 1,000. Now, just real quick, like you never should have typed that. I'm saying that from my perspective as somebody that understands this, but you don't grow, you're going to understand something. So if you're asking me to understand direction.
Yeah, I was just trying to get it. But get an idea of what they're about.
You're trying to find the license for, but can you drop pictures with that fast enough? C is kind of annoying because it's really just like, what's the find 68% for this. 68%. So, create it this much right here. So we're looking for a z-score of 50 plus. So how do I get from, how do I get to turn from to the left? So that's what you can get. Z-scores. Use the area to the left. You have a nice structure. So that's that same thing. Like, that actually makes sense. Because here is 34%. So 50 and 34 is 84%. So we have less than 40%. That's 2.5. Okay, we're gonna fire the machine up again. We got a few more things to talk about. So drop the shoe. Area, and this is the same, the probability is 0.5826. The area is 0.5826. But notice it says the z-score is greater than that. So there's kind of two ways the area could be that. It could be like this. So back here. So pass that a little bit. And so that would be the area to the left. This says And notice the inverse falls to the area to the left. It's the 100. That's why we have to draw this picture.
Okay, so what is that? One.
Problem is, you gotta decide, are you talking about zone show or show? Because this is affecting the show percentage. So then you drop it, show. What you just found is the probability that 76 people don't show. Which is, 76 people don't show up. I wouldn't worry about that question because I'm not going to give one away from the. It's the person who just said 76 is like, yeah, not a bunch of them. Yeah, I'm only going to get small. And that is tricky because it's talking about percent of people don't show up. So the question is, show up. And I mean that to be tricky, but it is. Won't be worded that way, but.
Okay, let's take a look at something else from yesterday, Monday. Everything we've just done so far here was finding a probability, not being given a z-score, but being given the mean, the standard deviation. We are always looking for probability. That's why on your note sheet, it says, normal CDF returns the probability between some limits. That's why we did that every single time, because all my questions were, what's the probability of this? What's the probability of that? What's the percentile of this? But is there a place to return the limit defining an area? Inverse normal. Yes, let's go do some inverse normal stuff now. And this is in your assignment as well as on your test. What about inverse normal? Which basically takes area or a percent, and it basically spits out your location. And I'm using kind of my own language for that, but it spits out your location. So let me give you an example. So let's say you wanted to be in the top 2% or whatever. Showing dogs. You want to be the top 2% of dog show people. Which makes sense, right? Like I want to be awesome at something. Everybody wants to be awesome at something. Yeah, thank you. So I'd like to be in the top 2%. Do you see that as an area statement? Like this time I actually just told you the area right now. Before it was always like, what percent are you in? And this time I'm saying top 2%. So again, as a picture, then you'd say, oh, so you're talking about being over there. Notice I didn't say bottom 2%, right? Because that'd have been on the other side. So I want to be over there. Well, the question is, where is that? You see what I mean? That's what I mean by location. Like how good of a score do you need to get? I don't know anything about showing dogs. Let's say the mean dog show score is 20.7 and the standard deviation is 3.8. So that's the average score that somebody shows dog. They show a dog and they get a 20.7. And it's not weird to deviate by that from 3.8. And so the question is, what score do you need to get to be in the top 2%? Do you see the logic of the question? You also see that this is just as natural of a question as the questions we've been asking recently. Again, as a doctor, if this was top 2%, maybe this is for something negative, like people with some really bad health condition. So I'd like to know, again, from same discussion as Monday, what score defines that? Like if they're above this, then we're gonna, get them into surgery immediately. I had a surgery done once like that. I went in there and they checked me and they're like, dude, you're in surgery tomorrow. And so, I crossed the line, like wherever that line is. Whoa, that's not good. Get in there tomorrow. So we're trying to figure out what that line is. How good do you have to score? Do you see this as an inverse normal question because you already know the probability or the percent? So what's the syntax for inverse normal? Again, a lot of your calculators, you don't need to know this. I have to type the area to the left. Didn't we say that the other day? That's not good news. Why is that not good news for us? We don't know that. But that's not hard to figure out, right? Because they have to add up to 1. 1 minus 2% is 98%. So the area to the left is 98%. And then it says, put in the mean and the standard deviation. Well, the other day it was zeros and ones. Today we just put in the mean and the standard deviation. Now, before we even do that, do you agree this is way up there? Like, does it make sense this is about 2 standard deviations above the mean right here? Why do I say that? Because wasn't that top tail, if this was 95% for the middle 2, then doesn't that leave 5% to be split here and here? So if that's 2%, this is about 2 standard deviations away. So if I took this plus a couple of these, that's pretty close to the answer I'm looking for here. Do you agree with that? Again, I'm talking about thinking. Do you understand what you are doing? Not I push buttons and answers come out. But if you can't reason this out a little bit, then you're really not ever going to be able to use this for anything. You're not going to benefit from this. You'll pass this class and get on with your life, but you're not going to benefit anybody by it. You're not going to advance in your job like you could, so to speak. So I'm trying to teach you how to think and understand this deeply enough to do something. So this is not hard. Inverse normal. It asks for the area on the left, and then the syntax is the mean, which was 20.7, and the standard deviation, which was 3.8. I typed that in, and I'm going to get, well, as I said, I'm going to get something kind of close to the mean plus 2 of those standard deviations. I bet I'm going to get something like 28.3, somewhere around 28. You see what I'm saying? Does that say 3.8 or does that say 3? Yeah, something on my screen. Okay. So second distribute, inverse normal. Again, I have a nicer calculator, so I don't have to type it in this order. It kind of tells me what to type in. This calculator is even nice enough that I can even say left, right, center. So I could actually type 2% and click right, but very few people have this nerdy calculator. I'm just going to type what you're typing, which is 0.98, mean 20.7, standard deviation 3.8. And when you hit paste, you see this is what you see on your calculator, right? Except for that left at the end. You see the syntax that I just told you. It does it for you. And again, the idea is this is hard for people to memorize. And so why not just ask them questions and then it puts it in there for you. And sure enough, I get something around 28, just like I said I would. So on a test, if I ask you that and you box that answer, what if I went one step further and said, what does that mean? Can you answer that? Like, again, I think you can't. You're wasting your time in this class. Like you have to understand what you just did. Just getting the answer right. You're going to feel good, right? If I give your test back and you get 90% or whatever, you're like, yeah, I did great. I agree. I'm high-fiving with you on that. But if you don't understand what you just calculated, can you use this for anything in life? The answer is no, nothing. You're learning really nothing. Again, I'm just challenging, how do you approach education? This is true for all classes, not just math. And of course, it's easier for you to do if it's a subject that you kind of like. If you like poetry, then when people talk about poetry, it sticks in your brain better. If you like math, that's going to be a more natural thing to do. If you don't like it, my worst grade in college was studying Greek mythology because it's not real. And I'm not a realist. So I'm studying Zeus, and it's like there was no place in my brain for that. This isn't real. I'm studying something that doesn't even exist. And I'm probably small-minded, but I got a terrible grade in there because it was just not sticking in my head. I wasn't able to make any sense of it, so I didn't really learn anything.
So what would that be, 28.5 wins to be in the top 2%?
Yeah, so if this is points, if these are points for your show, you'd have to score above that. You'd have to score above that to be in the top 2%. If you got exactly 28.5, you'd be right there. But if you got like 30 or 32 or whatever, then you're in the top 2%, maybe even higher. So you have to score above that is the simple answer to that question. If you score above that, you'll be in the top 2%. Do you see that that's a bit of a practical question? So notice what's cool about this is this did not report a Z-score. That's what it did the other day in your assignment. It said kind of confusingly, I'm not going to write this up here so you can see this later, but it said something like, what's the probability that your Z-score is above some certain number? They put C there to make it even worse. And they said something like that. And so notice again, that's the probability of something happening is 2%. And so they want to know what the Z-score is. My point is, if I returned to you here and said, hey, your Z-score has got to be a 2.2, does it make sense that's not near as helpful as saying you better score that many points? That's why ultimately yesterday wasn't near as relevant as today is. I'm not answering a Z-score here and saying 2.1, a Z-score of 2.1 will get you there. Because you don't know what that means. What does that mean? Okay, great. So how do I do that? What does that mean I have to score? Well, this is actually reporting the actual score for that. Let's do another example. I've told you before that the mean body temperature, I think we decided was like 98.6 degrees. And I forgot what the standard deviation was. So I'm just going to make something up. Say it's 1.2 degrees. So these are for temperatures. So what temperature defines the 11th percentile? So for some reason, you or some doctor wants to define the temperature that puts you in the bottom 11% of sort of coldest people, temperature-wise. Again, I'd like to give you a second to see if you can figure that out yourself. Draw a picture of that. What does 11th percentile mean? Again, just like a second ago, I said top 2%. Anytime you see percent, hey, look, I was just given a percent, 11%. This is going to be an inverse normal question because you already know the percent. Normal CDF tells you the percent. You already know the percent. Notice I didn't say bottom or top. That's tricky, but you got to know what percentile means. I didn't tell you that. I didn't skip that on accident. Percentile is already telling you that. If you're in the 11th percentile, how is percentile defined? It's left. As I said before, percentile is always left. If you're in the 96th percentile, that means you're higher than 96% of people. If you're in the 11th percentile, that means we're talking that right there is your 11%. Remember, what does that mean? It means you're higher than 11% of people if you have this temperature. But you're lower than 89% of people. 89% of people run hotter than you do. So, inverse normal. Do I use 0.11 or 0.89? Being on your note sheet, what area do you have to use for inverse normal? No matter what, area to the left. Last time, for that reason, we were not able to use our 2% that we were given. You don't just mindlessly stick that number in. We had to use 98%. This time, however, we are given the area to the left. So I just get to use it. Again, unless you have some fancy calculator. Mean, 98.6. Standard deviation, 1.2. Again, what we're going to get this time is not a z-score. We're going to literally get a temperature. A temperature below which puts you in the 11% of coldest people. I'm just going to retype the previous command. Type over the top of all my other stuff. It's probably a dumb idea. I got 97, however you want to round it, 97.1. So a second ago, I said, what does this do? It takes an area and spits out a location. What is the location? It's not a very good word choice, but it's like, what's the temperature that defines the 11th percentile? 97.1. If you're above that, you're in the upper percentile. You're in the 89th percentile. If you're below that, you're in the 11th percentile. So if that was your score, 97.1, then you're in the 11th percentile, meaning you are hotter than 11% of people. So again, do you see how much more helpful that is than a z-score? It's like, don't tell me the z-score is negative 1.6. What does that mean? Like, what temperature is that? It doesn't really do me any good. This is cool because it's literally spitting out a temperature. Let's do one more slightly just more visual example. Let's do this one. This one's awesome. I got this data from the other teacher at the other campus. I don't know where this nerd found this, but there is 3,276 different data points in this list. So notice 1, 2, 3, 4, 5. If I go all the way down to the bottom, notice 3,272. There's a lot of data here, and it's totally scattered randomly. Can you tell it's not in order just by looking at what you can see? And so this is samples of water taken from different water bodies as to how much carbon is in them. And it apparently is milligrams per liter. How many milligrams of carbon, which is a weight, isn't it? Milligrams, a weight, yeah. How many milligrams of carbon are in every liter of water? Now, I don't know physics, or I don't know chemistry enough to know is that good or bad. Seems like organic stuff is like leaves, so what do I care if there's organic stuff in there? Maybe I do care because it's like dead frog feet and stuff like that. That's organic. Whatever. Does it make sense that this might be normal? Notice I said might. I actually don't know. If you made a bar graph of all of these, would that be normally distributed? Again, to me, it feels like it would, just because wouldn't there be some that are, like mostly this is the way water is, and occasionally get something that's really full of organic stuff, and then some that is really clear and so forth. It feels like it'd be normal, doesn't it? But again, I want to caution you, in the real world, do you just apply what we're doing to any data you see? The answer is definitely not. Everything we're doing here applies to normal distribution. You got to show that that's the case.
on your final project, for instance, you got to graph this, you got to make a bar graph of it. So look at that, looks pretty normal, cool. All right, now we can make all these cool calculations.
So this is where I figured out, and I made myself a little note here to grab everything. But again, as I said before, we need to know the mean and the standard deviation. And how would you like to do this by hand? 3,200 data points. Woo, that'd be fun. Equals average. Let's see, click the cell, click end, hold shift, click the down arrow key. So there's actually 3,275 data points. Boom, it just tells me the answer without any trouble at all. I'm assuming this is like every lake in the country or whatever. So I'm going to do a population standard deviation. Although, can you appreciate if you divide by 3,275 or 3,276? Remember, that was the only difference between the population and the sample standard deviation formula. You're almost going to get the exact same answer. Click and shift down. Ooh, baby, that is sweet. And how should these be rounded? Don't say this out loud, but again, this is the kind of thing at the end of this class I'd be grading down for. Data points over here. What kind of data do we have? Should be 3. Notice this one apparently came out like 2 places, like I didn't have to round it off, like it came out even. That's kind of surprising, but whatever. Now, again, this is kind of what the test is going to look like, except for I'm going to tell you the mean and the standard deviation. That's kind of what I've been doing the whole day. So let's answer 2 questions about this. I'm going to write that down and then switch pages. 14.28. I am concerned that there's, and I did your last lab, if yours was in by the time I started looking at them, I asked you on the last lab, you know, what does mean in this context? What does standard deviation mean in this context? Make sure you're looking at my comments on that stuff so that you're growing, so you can ace the test. That's why I'm grading that stuff. I'm not grading it so I can take points away from you or give you points. I'm trying to teach you how this stuff works. You should be able to explain now that this is what you would expect. That's the expected value. If you went to a lake and measured it, this is the best guess. This would be the center of the normal distribution. This is most likely. And of course, what caused this is lots of scores higher than 14 and lots of scores lower than 14. How much higher and how much lower? Well, that's what this tells you. It wasn't weird to be 3.3 above that, 3.3 below that. That's what standard deviation means. It's that simple. Typical deviation. Typical deviation from this, 3. That's all you got to understand. So, 2 questions. Think of this as like a quiz today. I'm just gonna tell you the answers to these and not say much about them. hopefully now you could answer those two questions. 'Cause that's exactly what tomorrow is going to look like. It's also what your homework assignment looks like. Again, check with your neighbor, get both answers, right or wrong, put something down. There's the right answers. I'm just telling you what I typed to get this. '90th percentile is the area to the left. Can you appreciate that somebody would ask this question to kind of define, what are you might be asking this because you're interested in the 10 dirtiest water sources. So in other words, if you have a score above this, if you went and measured it and your score is above that, then you're in the top 10% of most polluted, or whatever organic means, most polluted sources. And so now we have a measure for that, super practical. Maybe this person's asking the same question. What's the probability a lake is above 18? Notice it's kind of an unfortunate coincidence. They also almost came out the same. But what's the probability a lake's above 18? 13%. 13% of our lakes are above 18. Notice this is 10%, and that's why that number is a hair higher. 18.5 is a hair higher than 18. So these ended up kind of similar, just by accident, if you will. But I hope you see those as practical. I hope you see those as, this is not something everybody can do. And although this is a really hard 200 level math class,
Like you may not have this mastered, but it's like there aren't a lot of people walking the street that could do stuff like this. And you learn a lot, even if you're not doing as good as you want to do. But it's a pretty big lift, you know, to figure all this out. And what have we been here, 5-6 weeks? Go ahead. Melissa.
I just had a question about the way you run that. Like I was inclined to put 0.13, and then since the measurement was in milligrams per liter for the second decimal place, I rounded. My answer came up 519.
Yep.
Is that something you're gonna mark on the test?
No, I probably will say nothing about rounding on the test because I really don't care that much. And as you know, it's annoying in my open math because if you don't pay attention to exactly the way it said to round it and even exactly the same way it said to write it, like parentheses with a comma between, if you don't read everything, you end up with it wrong. So yeah, a much better answer to this would be, you know, saying milligrams per liter, because if you don't put a unit on that, it doesn't really speak very much. And then we often write probabilities out to 4 decimal places. So I chose to do that. But if somebody had answered this 13%, good for you, same thing. So yeah, rounding, totally up to you. 18.519. So if somebody said, I think I'll carry that out to 2 decimal places, because if you remember the data was carried out to 2 decimal places, then maybe that'd be kind of cool. So remember, and we won't do this because I want to give you some time just to kind of work on stuff and ask me questions, but it'd be kind of interesting to go see on that original data list, are 90% of the numbers actually below this? Isn't that what that would predict? It'd be kind of interesting to put them in order and see if 90% of them really were. One thing that's kind of tricky too on the test and also on the review that I want to point out is, let's do something with this number. Just because we got 13%, okay, so how many lakes is that? If N was, what was it, 3275? It's one thing to say 13% of them, and that's great. If I said 13% of my patients have some disease, but remember, you have to plan for that. Like, if those patients are going to come in and see you and they're going to need a drug, then you can't just say I need 13% of this drug. I need to have enough injections to give that many people. So how many lakes is this? What do I do to that percentage? And by the way, this is a good argument for leaving it out to a few places, because actually that 0.04, although that's a tiny number, this 3275 is so big, maybe that'll actually make a contribution. 0.1304 times 3275. That's actually 427 lakes. Now, again, do you see this as practical? If your job is water quality and you say, okay, we're deciding for whatever reason that 18 is not good, like let's not drink that. Okay, 13% of lakes are in that situation. That's good to know. That's cool. You could be done. But if you live in an area with, 3,275 water sources or whatever, that means 427 of them are actually bad. That's how many we're predicting to be bad. That's, whoa. So do you see why it's kind of cool to take the percentage and do something with it? As I said in class to a few of you the other day, it's kind of like saying, hey, you get 30% off today on clothes. That's cool to know. That's a good deal. I'll buy it if it's 30% off. But at some point, you got to go to the cash register and say how much money it's at, right? You can't just leave it at that. So a percent times an amount. So there's a number of review questions on the review that kind of deal with that concept as well. Okay, I'm going to shut up. Leave if your brain is full. I recommend that you ask me review questions and discuss things, though. The test is tomorrow.